Okay, so happy Friday. So today we'll look at the exam a little bit. We'll go through that, and then if we have time, I'll introduce some more receiver concepts. We'll kind of drill down a little bit closer to implementation of an actual receiver, right? And kind of, we've been spending a lot of time on math and concepts and that type of thing. So that's the plan. Let me go ahead and let's see. I'll just share my screen there. And okay, so the test. I had some technical difficulties last night, and I was halfway through grading and marking up the test with lots of feedback and that type of thing. And then Adobe crashed on me, and I lost almost everything. I should know better to save more often, but I was trying to be in a flow and paid the price for that. So I graded regraded the papers this morning and got the grades posted, and but I didn't have a lot of time to give people a lot of feedback on their tests. So I did email the test, try to figure out how to upload them in Moodle, and just press for time. So I just emailed everyone. Hopefully that'll work for everyone. So overall, I just graded that out of 100. The average was around 75. As it turns out, people tended to do either really well or really poorly, and so no one should panic. But yeah, I think for some people, you'll know who you are. You'll want to I'm sure everyone has their own story on if you didn't do well on this test, and that's okay. I understand life gets in the way sometimes. You got to juggle different priorities and that type of thing. But I'm here to get you there, get you across the finish line. So we'll work together on that. I will probably, figure out some sort of either additional extra credit in a form of some sort of project, or maybe we'll do situation where maybe we can drop the lowest grade or something. I'd rather not do that, but so we'll figure out something. So don't want anyone to think, oh, all is lost and I'm going to be here another semester, whatever. So it's not going to happen unless you let it happen. So that's sorry to come across a little preachy on that, but I just really want everyone to be successful. But there's no gimmies here either, right? So all right, so let's go through this real quickly. This is the first time I've taught this course, and as you all know, this is all last minute and that type of thing. So sometimes when you write a test, you find out that people read into questions something that you didn't anticipate and stuff. So I'll cover some of those issues as we go through it. So but here, what is that term that Claude Shannon used to quantify information in the field of information theory? So so the term I was looking for is entropy there. And I tried to give you a heads up on that in my preview. My question one in the test preview was describe what is meant by entropy in information theory. So, I want you to take my previews seriously, and I think this would have been an easy one. I was surprised at how many struggle with this. If you put random or something like that, yeah, you're on the right track there. But really looking for this particular word. So if you came close, you got something out of that. Shannon's capacity theorem as a basis, right? So I'm telling you, which equation I want you to base this on. And this is where I say I'm going to provide you the formulas, and I did for the most part, but you gotta be familiar with them still, right? You don't have to memorize them, but you should recognize this one as Shannon's capacity theorem. Some of y'all had troubles with identifying what the B stands for. That's the bandwidth. And the idea here is that if you want to increase the capacity of a communication system, you either need to use wider bandwidth, which allows you to send more data through, or you got to increase the signal power or get rid of your noise, right? So and I was looking for you to recognize and describe what these terms meant. B is in bandwidth and that type of thing. So next time, consider that. When I want you to describe it, I mean, go into some level of detail there. So this B here, this is really kind of a probing question to see how much you really understand the trade-offs that are implied by all the things that we're learning here. And so it's a bit open-ended, but the idea is that, well, why not just keep using larger and larger constellations? When we do that, what we're doing is we're cramming more information into a fixed bandwidth. So it's not, the bandwidth's kind of given, but if we group more bits into a single symbol, then we're able to get more information through in a given allocated spectrum. But the issue is that our constellation is either getting larger, which means our energy is approaching infinity, which we can't do, right? So that's like the fundamental, the easy answer to it, right? To this question is that it would require infinite energy. Conversely, you could say that, well, given a fixed energy in your constellation, then all those dots are getting closer and closer together, and eventually you would need zero noise in order to be able to distinguish them. So that's really the kind of level of understanding I was looking for here. Okay, so by the way, I assigned 2 points to this first question, and then about 6 points to the second question there. The third question, what is responsible for adapting the information to the available communication media? Well, the available communication media is described by the channel, right? And the thing that we're adapting, using to adapt the input to that channel is a digital modulation. So a lot of y'all put the channel encoder, and that makes some sense too, even though we haven't really described it yet, other than me saying that, we put in some redundant bits, kind of like parity bits, parity check bits. And so that does help you overcome some of the challenges in the channel. So I accepted that also. Some of y'all had a pretty deep understanding of each of these blocks, and you actually wrote those out, and that's great. But make sure that you answer the question and kind of identify that specifically. So name 3 features of a signal that we can
say louder. I have a question.
Yeah, what's up?
How many points was the question 3 worth?
Oh, question 3 I made worth 2 points.
Okay, thank you.
Kind of, I did that one after the fact a little bit because people had so many troubles with that. And I hate, some of these are intended to be, I think they're going to be easy, and it turns out that they're not. And okay, we'll
You circled
together.
That one?
What's that?
Okay. Is it okay if I circled my answer for that one?
Yeah, I tried to do that. So if I miss that, let me know.
Well,
Okay. So yeah. So sometimes I think questions are going to be easy and then they're not, and or people read into them a different thing than I intended and whatnot. So I'll adjust things accordingly. I hate to have a question like this that, well, if you know it, that's like this first one. If you know it, that's an easy 2 points. But if you don't know it, then you just lost 2 points, right? So trying to be fair there. All right, so back to question 4. The things we talked about in class, the kind of first level of things that we modulate are amplitude, frequency, and phase, right? So all those different coefficients that you would see in like a cosine omega t type of signal. A represents the amplitude as a coefficient of that cosine. Omega t, omega can be modulated, and then we can also have a plus theta, and the theta can be modulated. And those are the things we talked about so far. You may recognize that from perhaps embedded systems or data communications or something like that, that we also can work with time. And so some people put in pulse width modulation, or there's other things, pulse position modulation, things that you're modifying the T aspects. And so that's a good observation, and I accepted that also. But in RF communications, which is kind of what I'm emphasizing in this course, it's legitimately not the only type of communications, but wireless is what I'm emphasizing. Then we're generally working with amplitude, frequency, and phase. We will get some more complex things. So randomness. All right, I'm looking for some examples. I'm looking for 3, 3 different ones, not just kind of randomness, right? I want you to get specific on these type of things. So, I'm sorry. 4 was worth 3 points. 5 here is worth 5 points, and so yeah, there's lots of different things here. So I was pretty liberal there. As long as you tried to put down 3 things, that was good. What does the term white imply in additive white Gaussian noise? We struggled with this one also, and really what I tried to mention several times throughout the course, that where we came up with that term white is an analog from white light, and it's where the white light is composed of a roughly equal mixing of all colors, and includes at least what we think of as a visible light spectrum, right? And so this AWGN, the additive white Gaussian noise, the white refers to the fact that this thermal noise is has a flat spectrum, and it's roughly infinite. It's technically not infinite. That would require infinite energy in that, but it doesn't roll off until above frequencies that we're interested in. So that's really what I was looking for. But yeah, a lot of different answers there. So okay, now six was worth 8 points here. You had to do a little calculation, possibly. So I gave a few more points to this one. This is, don't read too much into the problem, but read in what you need to, right? So you want to observe that it's a uniform random model. So I shouldn't be seeing things like Gaussian or the equation for Gaussian or that type of thing. I should be seeing uniform. And it has support. So that's a bit of a technical term. I used it in lecture, but I tried to clarify it. So if you did recognize that, great. But if you didn't recognize what I was meaning by support, you should be able to conclude here that it is, has some value between pi over 2 to 3 pi over 2. And then I'm asking you to find a mean. Well, if you understand a uniform random distribution, and you've seen the limits, then you can kind of do this by inspection. You can just average those two, and you don't have to do the integral or anything like that. Just average pi over 2, 3 pi over 2, and you'll find that the average is pi. So I think few people recognize that. Just wrote that down. That's great. But if you didn't, then you go through and do it fundamentally, right? So now we're going to observe it's a uniform distribution, right? I said that. So you come here and you pick up this f of x. That's now within this range. So pi over 2 to 3 pi over 2, it's going to have a PDF or an f of x of 1 over b minus a. So 1 over 3 pi over 2 minus pi over 2, right? And now we want to look at the expected value for a continuous random variable. Now we're going to take that f of x and we're going to substitute in a dummy variable. And we're going to multiply that by that dummy variable, right? So this is the integral from minus infinity to infinity of alpha times f of x, or this 1 over b minus alpha there, times d alpha, right? So and so let's come down here, and so you just kind of plug and chug. That's the denominator is your limits, and that's that PDF 1 over that b minus a, right? And you don't have to integrate from minus infinity to plus infinity because it's 0 everywhere outside this pi over 2 to 3 pi over 2. That's the nature of a uniform distribution. And so really you're just integrating alpha d alpha. And we know how to do that. That's 1/2 alpha squared. And this is just simplifying all of this to 1 over pi. Okay. And then substitute in, and sure, you get some square terms, but they cancel out and you end up with pi. So a few people did it that way. A few started, couldn't figure out how to finish. Some people forgot to add the alpha out front there, or some didn't, recognize this as the f of x. But that's how to solve that problem. Yeah. So then 7 here. So here, how many different symbols are required? So I don't know if this was confusing but I still think it's clear, but a communication symbol maps 4 bits to a set of symbols, right? So you have K equals 4 bits, right? So how many M is that? How many different symbols are needed? Well, yeah, that can be 2 to the 4th equals M. That's basically taking this equation, right? So we know that K is 4. What is M? Well, that's log base 2. How do we get rid of that log base 2? Well, we take each side to the power of the base there. 2 is the base. Same type of thing you do in base 10 logarithms. This is just base 2 logarithms. And I'm sure you had some exposure to this in embedded systems. So try to, reach back into that memory and try to connect these things here. But you've got 4 over here. So if we raise this equation, then it's 2 to the 4th. M is equal to 16 then, right? If not, you can just kind of play with it. Hopefully you've worked with these numbers enough so far that, 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16, right? So I tried to keep the numbers small so you didn't need to do any craziness there. Now this is similar to the homework problem, and I think I kind of had a little bit of confusion on the solutions at first that I posted, and I realized, I had flipped it around, right? So that was a careless mistake on my part, and hopefully I didn't confuse you too much, but and hopefully I got it right this time. But the idea here is that if we have 1 megabits per second coming in, that's 10 to the 6 bits per second coming in, each 4 bits coming in gets grouped into 1 symbol going out, right? So there's a 4-to-1 ratio there. You don't need this relationship anymore to solve this problem. You just know that there's 4 bits coming in that gets mapped to a set of symbols, one symbol. So that's just one megabit divided by 4, 250 kilosamples per second. Okay, so 7 was worth 8 points also. All right. Question 8. This is pretty much, I just copied it from our PowerPoint presentations that we did in lecture, and didn't ask you to derive anything or whatever. It's just a matter of understanding that these 2 diagrams convey much of the same information. A trellis can actually show things how things evolve over time, right? Whereas the state diagram is kind of one instant of time and showing how you might move to the next state, right? Here we have kind of each vertical slice of this is one instance of time, right? So this might be T0, T1, T2, T3, T4, and we can see how things might evolve over time. And that'll be important if you study, some fancier detection techniques, like called the Viterbi decoder. And you want to see how the system transitions from state to state over time. If you kind of got this concept right, even if you just put maybe one transition here and you attempted to label them, you got most of the points there. Just understand that all of these are transitions, and should be labeled in some way, right? So not just the ones that go from one state to another, but if you get a 0 in this state, you're going to stay in that state, right? So we need to describe that on the state diagram and stuff. So it's the same thing over here. If you're in state 1 and you get a 0, then you're going to stay in that same state. So to fully label the corresponding trellis diagram, it'd be good to have something on each of those, right? And as we recall from last year's courses, or perhaps a year before, I'm not sure, that when we draw these state diagrams, whether up here or down here, I imagine you spent most of your time looking at this type of diagram. This is the input that you're getting, right? And this is reflecting the state or the more of the signal, right? So, all right, 9. We didn't reinforce this knowledge a whole lot here. I did tell you that I was going to ask, on the preview on question 12, FSK modulation. What is the closest spacing to still have orthogonal signaling? So that's pretty much what I asked there and stuff. So but yeah, we can review this concept here if need be, but a lot of y'all recognize this formula. It's a very simple formula. Maybe it was too simple and you didn't recognize it as applying to the FSK modulation, but sometimes engineering problems are simple, right? And it took us a little while to derive this, but this is the answer here. The trick is some people got the idea of rate versus period mixed up. So okay, that's you were close. But when you do problems, try to make sure, and I know you don't have a lot of professional experience to understand, hey, is this a reasonable number or not? But yeah, when you can, you crank through your formula and then look at the answer and say, does that make sense, right? So if we're modulating at 100,000 symbols or 10 kilosymbols per second, then our spacing being 50 kilohertz or 50,000 hertz, that sounds reasonable. If you get this mixed up, you end up with something that's like in the millihertz or microhertz region or something, and that's probably not reasonable, right? So, but you got hopefully I gave you decent amount of credit if you just missed that, as long as you identified the formula to use. So let's see, question 9, I assigned 8 points to that. 10 here. So all right, so I got there's a mea culpa here. I had intended to try to keep your formula simple, and I gave you kind of a simplified version of Bayes' theorem, and it's a little bit too simple. But this question was the same as your homework, except instead of 3 different interferers, there were only 2 to keep it simple. And but you really wanted kind of this equation here, the denominator, reflecting the overall probabilities regardless of the inputs and stuff. So if you tried this one and you identified that you need to be using Bayes' formula or something like that, you got I think 16 points total out of this. So I didn't worry too much about that. But yeah, you still need to kind of identify that it should be Bayes' theorem. You did this in your homework, so hopefully it looked very familiar to you. I just changed some numbers and used A and B and stuff like that. So for most of you, that was some easy points, even though hopefully you didn't struggle with that too long during the test. If you do see this in the future and it's like you feel like, I don't think you put the right formula down on that formula sheet, then yeah, ask, and I'll take that into consideration, and I'll let you know the formula during the test. So don't spend 20 minutes on a problem banging your head against the wall during the test. Just say, hey, did you forget, professor? Did you mess up? And sure, I can fix that. All right, 11 I gave 6 points to. That was a little hard because boy, it's a single question, and it's almost an all or nothing type of thing. But maybe I did give some partial credit if you were in the right area. But we struggled with this one, right? So the maximum likelihood receiver is a little bit simpler than a map or maximum posteriori probability receiver. And when we derived these, we did the map receiver first, and then we noted that if the inputs are equal probable, then we can simplify it, right? So it has nothing to do. So I had the word complex in there because the receiver is a more complex receiver, but it has nothing to do with complex data or anything like that. It's really when those symbols are equiprobable. And so just we can reinforce that. Maximum likelihood is simpler, but it does require that the inputs are known to be equal probable, right? So that might would have to be known at the design of the overall system, right? So if you know that, yeah, there's an equal probability that the bits are going to be 0 or 1, or if it's 0 0 0, then that's as equal probable as 0 1 0 1 0 1, or whatever, right? So that all the bits that are mapping into this thing as symbols are equal probable. That's an important thing to observe. It doesn't always satisfy. It's not always held, but when it does, you got to know it up front, because you're going to design your system accordingly, right? You're going to design it so that it is a maximum likelihood receiver, right? So then 12, what is the constellation? So I give you this constellation. What is the decision area boundaries? So got some creative things there, but really these are the boundaries, right? So if we remember, we had this kind of rule. So I think you could maybe draw this by inspection if you don't, if you just look at it. And don't get lost in the rules and that type of thing. You can kind of say that, yeah, if I'm trying to figure out how to partition this space so that I can conclude which one is which, this makes sense, right? I hope this makes sense to you. That these are the boundaries. This is going to be the area that goes on up here forever, right? And that anything that falls in this area is closest to this 00 constellation, what I've labeled as 00, right? And also, but if you do want to apply our kind of rule-based approach to this that we derived, then you connect these constellation points, and then you draw a line that bisects that connecting line in a normal or perpendicular fashion, right? So you could connect this 00 to 10, and then you would sketch in a line that would bisect that, cut it in half at a normal direction, right? And then you do the same over here and kind of draw this in, do the same over here and draw that in. You would see, oh, this is collinear with this line. So let's just make that one continuous line. And then you would connect these 2 points and draw in that normal bisector there and notice that, oh, that's collinear with that line. So let's just make that one line, right? And stuff. So sketch the decision area boundaries. That's really what I'm looking for. And then label each constellation with a gray code. You did a gray code in your homework, and that was a little bit more complex. I think that was a 3-bit gray code. This one's a 0-bit. Even if you just try to do it brute force, it will only take you a couple of tries. There's not that many combinations. But recall that a gray code is the type of code where only 1 bit changes at a time when you're closest between the closest constellations. Now, I think in the homework solution, I said, yeah, pick a point and then go clockwise and write it out. Well, that's one way of doing it. You can go counterclockwise. You can go in any order you want. What's really fundamental here is that when you're referenced at one point, what is how do the bits change on those closest to it? So if you had 00, 01, 10, 11, if you just did it in binary order, then yeah, you're seeing 2 bits change in this transition. These closest things, this one would be 01 and that would be 10. So both the first digit and the second digit are flipping there. And then also between these two, right? So this would have, if you had done this in binary order, it'd be 11 and then 00. So both of those digits would be flipping. So the reason why gray code is important is that we're doing our best to estimate this symbol, right? But that symbol corresponds to some bits. That's ultimately what we're after, right? We got to estimate the symbol first, and then we got to look up what that symbol means in terms of bits. In this case, we have a 4 PSK, k is equal to 2 in this case, right? So, what we want is if we're wrong about this, we're likely wrong either by thinking it's this symbol or this symbol, right? If this is the real one, but it's noisy, it's distorted, we're wrong, then maybe we guess that one, maybe we guess